So, welcome. I think it's time to start. We're going to say it's time to start. Is it okay if we start now? It's okay if we start now. Let's start now. So welcome to my talk, Understanding Probabilistic Data Structures with 112,092 UFO sightings. Quick show of hands. Who here knows what a probabilistic data structure is? Okay, I can't see any hands up because there's light shining in my eyes, but it looks like no one has raised their hand. So what that means is that I am a complete expert on the topic of probabilistic data structures, and so you should trust everything that I say. No. I never claimed to be an expert because I actually hate the term expert because it says so much without saying anything at all. It's just a dangerous term. But this is a talk about probabilistic data structures. My name is Royse. I am a developer advocate at Redis. Perhaps you've heard of us. We seem to be popular. There are three things on this slide that matter. One of them matters to you, one of them matters to me, and one of them matters to my boss. Any guess what matters to my boss? Right there. My boss wants you to know that Redis is more than a cache. That's probably what you've been using it for. It makes fantastic cache, but it has a lot more capability than just storing serialized Java objects. So, one of the things it can do is probabilistic data structures. I'm not going to belabor the Redis bit. I'm going to go dive deep into what probabilistic data structures are and how a couple of them work at the lowest levels. And I'll show you quickly the commands to use some of these probabilistic data structures in Redis. Also, I will say the word probabilistic a lot in this talk, and I will probably get it wrong. It's hard to say. So my boss cares about that Redis logo. He wants you to know that. Frankly, I kind of want you to know that too, because then that means my options turn into a big pile of money. The thing on here that matters to me is that Twitter logo right there, or that Twitter ID. So I have judged my value as a human being based on the number of people who follow me on Twitter. Perhaps not as much as I used to, but still, I'm kind of in for a penny, in for a pound, as they say. So give me a follow on Twitter if you're so inclined. I just post technical things and occasionally song lyrics from metal that I'm listening to. And the thing on this slide that matters to you is that GitHub logo, that GitHub URL. So all the code that I'm going to show you, all the slides and all that stuff is out on GitHub at github.com/GuyRoyce, and there'll be a QR code at the end that you can scan to get to that. And yes, I actually do have guy.dev as a domain name. So it's probably my greatest accomplishment after having children. And we are using Slido here. I'm sure you probably have all figured this out by now, but if you haven't, go to sli.do and put in GeeCON if you want to leave me any questions, and we'll get to those at the end of the talk. If there's something really, really pressing, I might try and look at my phone. I don't know. We'll see. So 112,092. That is a surprisingly large number. It is the number of UFO sightings that I have in a data set. And by data set, I mean CSV file. This was data that was screen scraped from the National UFO Research Center that is researching the UFO phenomenon in North America. Records go from the 50s to a few years ago, at the time that this data was screen scraped. So the guy who screen scraped this data is a wonderful chap by the name of Timothy Renner, and I always give him credit for this because I've gotten so much mileage out of his data. He has screen scraped UFO sightings data to do data science and data analytics with. He's screen scraped Bigfoot sighting data. He's screen scraped, which I get a lot of fun of because I make a joke about how Bigfoot's my dad, which obviously, right? He screen scraped the Haunted Places Index of North America. So all kinds of really fun data, right? And he screen scraped all these UFO sightings. For the UFO sightings, he decided to do some basic analytics to understand the UFO phenomenon. And so the first thing that Tim did was he decided to put them on a map and just see where they happened. Where do UFO sightings happen? And it turns out that about 80% of the UFO sightings in the data set occur within 100 kilometers of a US Air Force base. The other thing that was interesting is the day of the year with the most number of UFO sightings. Any guesses? Hint, this is America. 4th of July, that's right. Number one, by an order of magnitude on the histogram, it's like this is a spike in the middle of the year of the most UFO sightings. Now, I don't know about you, but if it's a day where we're launching fireworks and I see something in the sky and I say, Dad, is that a firework? And Dad says, no, son, that's a UFO. I need to find a new family. But this data is a lot of fun. You can go in and read some of the excerpts. There's a lot of really good ones. I got a couple stories of some of the UFO sightings that are in there. But you just go in and you read through them. The Bigfoot ones are fantastic too. But his conclusion after doing data science against the Bigfoot data set was that you could find Bigfoot in the woods. Who'da thunk it? So the data is actually pretty basic. We've got a summary of the sighting. So this is just sort of a brief description of what the UFO sighting was like. 3 saucer-shaped ships. That's fun to say. High in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. Sounds like a firework. He has the city and state where it occurred. This was in Salem, Oregon. Obviously, this data is from the National UFO Research Center in the United States, so they're all states and cities. It's got the date and time that it happened in convenient ISO 8601 format here. So this one happened on September the 15th of 1950 at about 2 o'clock in the afternoon. The shape of the UFO sighting is categorized. Things like disk, which seems kind of obvious. Object is probably the most common one. Oh, and light is another common shape. So shape is used loosely here. They have a duration in human terms, so like 15 minutes or about 2 hours or all afternoon. A link to the report, the full text of the UFO sighting, the eyewitness account, and then the latitude and longitude where they occurred. So this is fun data. You can do a lot of fun stuff with this. We're going to understand probabilistic data structures with it. So, what's a probabilistic data structure? That's probably the first thing we need to answer. I did a super scientific survey on Twitter like 4 years ago at this point, in December of 2019. And I asked everyone what it was, and I got 119 randos to respond to me. And they said 58% never heard of them. 22% had heard the term. So 80% of developers that are in my sphere on Twitter either hadn't heard of hadn't even heard of probabilistic data structures, or they had heard the word, but they didn't know what it meant. I suspect at least half of that 22% probably heard the term in the question I asked. These are developers we're talking about. It's like, well, literally speaking. The other 20% were split pretty much down the middle between knowing what they were and having actually used them. So, if you don't know what probabilistic data structures are, you're in good company. Most people don't. To understand what a probabilistic data structure is, I like to think about their evil opposite, their evil twin, the deterministic data structure. A deterministic data structure is a data structure that, well, it's all the data structures you've used all your career. If you took a data structures class in college or in university, then you probably have used these and written these. It's the lists and the sets and the arrays that we use all the time in our code. They're called deterministic because they do what you expect. If you put a value into an array and then you go and look for it, it's there. And if you put another value into an array, assuming you didn't overwrite the previous one, it doesn't mess with the previous value. And we use these all the time. And I'm going to dive into one particular deterministic data structure as sort of a review for those of you who have taken a data structures course. And if you haven't, then this will be knowledge earned. So, on hash tables. And the reason I want to talk about hash tables and how hash tables work is because the principles behind a hash table apply to probabilistic data structures we're going to talk about later. Sound good? That's where you nod vigorously and say yes. Thank you. So, hash table, as we all know what a hash table is. We're mostly Java developers here. That's a hash map. If you're a Python developer or a .NET developer, you have my pity. And they call them dictionaries. And if you're a JavaScript developer, which is actually what I tend to do most of the time, which means I go home at night and I cry. If you're a JavaScript developer, well, pretty much everything in JavaScript is a hash table. It's all just objects. And so the idea of a hash table is pretty simple, right? It's a key value pair. Given a key, get the value out. Give a key and a value to set it. We've all used these. And the reason they're called a hash table is because they use a hashing function. And you've probably heard of hashing functions too. But it's not necessarily the hashing function you're always thinking of. Usually when I say hashing function, people will think cryptographic hash. Those are hashing functions. But there are other simpler, more performant hashing functions that don't have the security properties that cryptographic ones do. That's the kind of ones, these are the kinds of hashing functions you want to use in a hash table. The general thing that a hashing table does is it sort of squishes all the data down until you just have a number, like a 64 or 128-bit integer. And so it takes some data and a seed, and sometimes a salt, and it pipes it through the function, and it can take 2 gigs or 2 bytes, and it turns it into a 64-bit or 128 or 32-bit integer, depending on the function. In here, I've got some data coming in. It's actually the ASCII values and the UTC, or the UTF-8 values for Scully from the X files. And it spits out this unique number. And every single time you do it, it's deterministic. Give it the number and the seed, it will always give you the same value. But you can't get the value back from the hash. That's what hashes do. And so in a hash table, what we do is we hash our keys. And so here in this hash table here, we've got a little data structure in memory. This is just an array of linked lists. I've arbitrarily made mine 10 long because that fits nicely on my screen. And when you put something in a hash table, you take the key and you run it through a hashing function, and you get that big wide number, 128 bits or 64 bits or whatever. And then you modulus it with what the size of your array is. And that will give you an index. So here, we do that computation on city, get a number, modulus 10, and that gives us the number 1. So we add to the linked list at position 1 the key and the value. If we come in and add another value, let's add state, and we can see it's going through the same process, but this time the state is put in the linked list in position 4. Sometimes you will run into a hash collision. So we want to add the value for shape into our little hash table here, and it's in index position 1 as well. There's something there already. Well, that's why we used a linked list. And so what we do is we add it to the end of that linked list. And so now in index 1, we have city and shape. And then when we go to read these, I think that's my next slide. Yeah. So when we go to read these, then we just reverse that process. So if we want to get the city out, we hash it again, get the index, and then we walk the list until we find city. So that's hash tables for dummies in 5 minutes. Actually, probably for smarties. So when we pick our deterministic data structures, we tend to be making trade-offs against time complexity and space complexity. So let's look at an array and a linked list. An array has O of 1 operations. It's constant time. You just go there and you get the value. But its space is fixed. It's O of n. If I've got an array that's 100 elements wide that can store 100 things, then it takes up 100 units of space. And so its space, it loses space. It wastes space a little bit. It's not as space efficient. A linked list, on the other hand, tends to be O of n to access it, because you got to start at the beginning and you walk down the linked list until you find the thing you want. But it doesn't waste any space. It only stores exactly what it needs. And so we'll pick our data structures depending on what our requirements are here. But that's not the only reason we pick our data structures. It's not always a time versus space. Sometimes it's a capability thing. So in the example of the array and the linked list does very fast insertions. The array, but it can grow indefinitely. The array is fixed, and so if you want to change it, it adds extra complexity. Or sometimes we just pick a hash table because we actually want to store our values with keys and values. It's just fundamentally useful. So we're not always making that trade-off in time and space complexity when we pick our deterministic data structures. But there's a third trade-off that we could make when we're determining which data structure we want to use, and that's an accuracy trade-off. So we can take a data structure that's super small and super fast, but it lies to you. It lies to you, say, 98 or 2% of the time. Yeah, not 98% of the time. What is it, a politician? Yeah. But yeah, they're data structures that will lie to you. And this might sound crazy, right? I want my data structure to be 100% accurate, to always tell me the truth all the time. It's like, well, do you always need that? What if you're, say, a large online video provider called MeTube, and you need to count unique views on a video, unique users viewing a video. You don't want to count a user twice. How do you do that? Do you create a big list of all the users that have watched the video and count it? That doesn't sound very scalable. Well, what if you could shove it into a data structure and that count was off by a couple of percents, but took 1/1000th of the space? Is that worth it? Does it matter whether it had 1,032,000 views or 1,034,000 views? Probably doesn't. This is the type of problem that probabilistic data structures is fantastic at solving. When you need something that scales and is fast, and you're willing to sacrifice that precision or that accuracy. They can be very precise, they're just not accurate. And if you think about it, you've been using these for a long time. Anyone recognize this photo? It was made famous by Richard Dreyfuss and Steven Spielberg and a pile of mashed potatoes. And if you get that reference, you're as old as I am. So this is the Devil's Tower in the Badlands in Wyoming. It's a gorgeous place. I've never been there personally. But this picture here is a JPEG. And if you look really closely in the top right corner right up here, see that pixel right there that I'm pointing at? Everyone see it? It's the wrong color of blue. Does it matter? No, it doesn't matter at all, because it's doing what it needs to do. We've sacrificed that accuracy, that fidelity, to make our image smaller, but still useful. So this is something you've been using all along. A lot of probabilistic data structures can be thought of as sets that are kind of unusual, that have some weird properties. Usually they're limited. So if we think of a set as a data structure, or even as just like a mathematical construct, you can add things to a set, you can remove things from a set, you can get things from the set, you can do unions and intersections and differences. You can ask a set if something's a member of the set, and you can count the number of unique items in a set, get the cardinality. And probabilistic data structures will let you do some of these, but not all of them. Some of them will only let you check for membership. Bloom filters work this way. It's one we're going to look at here real soon. Bloom filter asks the question, is this thing in the set? That's what membership is. We've got cardinality. That's just the number of items that are in your set. So if you were counting unique users on a video platform, you would want a set that would give you the cardinality. You'd want a probabilistic data structure that does that. Frequency sort of stretches the idea of the set a little bit by associating a number with them. We could call this a sorted set, I suppose, where each thing in essence has a count. So I've added the star 5 times or the square 4 times. And so this lets me count and get a frequency, and so I can get a sense of order. We've got rank, which is like frequency, but is simpler. The count doesn't matter, the order matters. And so one of the ones we'll look at the end of the talk, top K, does ranking. It also counts, but its counts really messy and not very accurate, and actually, honestly, not very useful. But the ranking is very useful. And so some probabilistic data structures will do this. And when we're looking at sets, we will look at ways to compare these sets. And we'll talk about Jacquard similarity here in just a short bit. So When it comes to probabilistic data structures, there's several choices. I just kind of went out to Google a few years ago and grabbed a few and threw on here to look at. We've got, this is just a list of some. There's Bloom filters and cuckoo filters. If you notice the little red dagger there on those, if it's got the little single dagger, that means it's part of Redis Bloom, which is included with Redis Stack. If it's got a double dagger, it's in Redis. So these are data structures you can use from Redis. The hyperlog log is the one here that is part of just open source Redis. Redis Stack, which is free and the source is available, but it's licensed differently under a Redis source available license. Those are got the double dagger. And the ones that are highlighted in blue, is that visible on the screen? I think that's pretty visible on the screen, are the ones we're going to talk about. So we're going to talk today about Bloom filters, min hash, and heavy keeper. Bloom filters will let you test for membership. So you can add things to a Bloom filter, and you can say, is the thing in the Bloom filter? And it will say no or probably. That sounds great, doesn't it? The min hash is not anything to do with Redis, but I think it's really cool. And it is it's a way of comparing documents. You can turn documents into these hashes, and then you can use a GeeCON similarity to compare those documents in a very performant way. And then the heavy keeper is called top K in Redis, and it's a way of doing ranking. It's great for like trending topics or perhaps network traffic analysis. Like, this IP address is hitting us the most. I wonder if they're bad actors or not. You can use it for things like that. I mentioned Redis Stack. This is the advertising part of the talk, so thank you. Redis Stack is honestly, legitimately, as a developer, this is the tool that I use every day because it's just regular Redis in a Docker image, ready to go, with several modules, extensions to Redis that we've added that are all free to use. So Redis JSON, Redis Search. So Redis JSON stores JSON documents in a tree in Redis. Redis Search lets you search those documents. Redis Graph puts a graph database in a key in Redis. It's one of my favorites, honestly. Redis Time Series is a time series, so you can put like stock prices or temperature over time and weather data in it. And Redis Bloom, which includes probabilistic data structures. And there's the URL where you can find it, but honestly, if you just Google Redis Stack, you'll find it. It's actually super convenient. I run it in Docker constantly. It even comes with a little GUI called Redis Insight. So let's take a look at Bloom filters. Who's heard of Bloom filters before? There's usually a few. Okay, there's a few of you. Not a ton, but well, good. So if you've heard of them before, you may have looked at them. You might be a little bit bored, but be patient. Everyone else hasn't heard about them yet. So Bloom filters, as I mentioned earlier, test for membership. They can answer no or probably. They have a fixed size. So when you create a Bloom filter, you optimize it for a particular number of items. Say, I think I'm going to put 1 million items in this Bloom filter. And then that's all it's going to be good for. If you put too many items, it'll lie to you, and everything will always be probably. It'll fill up. And every operation on a Bloom filter is O of 1. So very fast. Very consistent might be a better way to say that. Bloom filter is made up of two main parts. You've got a series of hash functions. I put 3 on here, and their corresponding seeds. And you've got a bit array of a fixed width. This is the size. I've chosen 10 bits, even though you would probably want to use whole bytes. But it, again, fit on the screen. And the way it works is that you can take data and run through these hashes like this. So we're gonna take UFO encounters. This is a great one. It's called Megatron in the Bushes. And there's these two guys were driving down the desert highway, I think in Arizona or New Mexico, somewhere in the American Southwest. And a necessary bodily functions need was made aware to them. They had to pull over and take care of something. And so one of them goes behind a mesquite bush to take care of their business, and he hears this weird sound coming from further into the desert that they described as sounding like Megatron from the Transformers. That sort of transformer sound that they make. And so they freaked out and hopped in their car and went barreling down the highway for like 75 kilometers, and these lights came up from behind the mountain and chased them, and they were totally not high. So anyhow, what we want to do is we want to add this story to the Bloom filter to see if we've heard it before or not. And so we're going to put Megatron in the bushes into the Bloom filter. And so we run that string through our hashing functions. And this will give us a hash value, a unique one for each function. And then we modulus that with the width of our Bloom filter, and that will give us an index. And wherever there's whatever indices we get, we put a 1 there. And so here we got 5, 0, and 6, so we put a 1 in position 5, position 6, and position 0. Now when we go to read the Megatron in the bushes thing and say, hey, when we test it for membership, when we say, is Megatron in the bushes actually in the Bloom filter? And so we go through that exact same process. We will get the same indices, and then we can go read them and say, are these all 1? If they're all 1, probably. If any of them are 0, definitely not. And you can see why that works, because the only way something goes from 0 to 1 is because you set it. And so if you go and check it again, and there's a 0 there, someone definitely did not put that value in there. But the reason it says probably is because, as you might imagine, you could come up with other ways to get this same combination of indices. So here's another one. We add a second value to the Bloom filter. I seen a UFO when I was about 13 years old. Grammar and Yelly case are directly from the encounter. So this gives us similar values. It gives us different indices, but we have a collision. Number 6 here, right? It's already set to 1. But that's okay, because when we ask about Megatron in the bushes, we still get all 1s back. And we ask, I seen a UFO when I was about 13 years old, we get all 1s back. And they overlap, but they don't fully overlap. And so our Bloom filter is still accurately telling us what's in it. Let's add a third item. Investigators from the Bigfoot Field Researchers Organization observed a glowing green-blue sphere. When you run this through, all of the indices clash with things that are out there already. So we add it to the Bloom filter, but the state of the Bloom filter doesn't change. Now, if we had asked before we added it if this was in the filter or not, it would have said probably. And if we add it and then ask, it's going to say probably. This is why it's probabilistic, because it's kind of squishy, right? It matters what order you did things in. Now, I mentioned earlier that Bloom filters will fill up. And so you can imagine here, we've already used 5 bytes, 5 bits. We've only got 5 more bits to go. Once this has all 1s, it always says probably. And so this is why you need to determine the width appropriately. So how do I determine how big I should make my Bloom filter? If I want to store 1 million items, how many bits do I need? And how many hashing functions do I need? Well, generally speaking, the more hashing functions you have, the wider it needs to be. But the fewer hashing functions you have, the more a collision will impact you. If we only used 1 hashing function, the second you get a collision, you're in we don't know what's going on territory. You get a lot more probablys that way. But it won't fill up as fast. And there's actually a formula to figure this out. And so just do this easy math, and you're good. Actually, there's online calculators here, but the 2 key things that you need to figure this out are the acceptable false positive rate and the number of items. And really what you do is you know how many items you want, and so you solve for K on the bottom. And then you then solve for P up top, and you take a guess at the number of hashes you need, and the number of bits. And if your false positive rate is acceptable, then you go with it and you don't. Or you just use an online calculator. That's the easier way. The other way to do this is just not code your own Bloom filter at all. And then you can use Redis to do that. So you can call BF reserve. That will create a Bloom filter using Redis Bloom. You give it an error rate. Here I'm saying 0.5%. And you give it a capacity of 100. And then it creates it. And then you can just call BF add and BF mad to add and multiply add to the Bloom filter. It's worth noting here that in the mad example, that it's returning a 0 and then a 1. That's because in the right here, I've added light already. And so it knows that that doesn't modify the state of the Bloom filter. And so if it doesn't modify the Bloom filter, it lets you know. So you can actually add and check at the same time, which is kind of handy. Saves a round trip. It's a very Redis thing to do. And then you can also call BF exists and then ask it if it exists or not. And there's a multiple version of that called M exists or mexists. I always feel like that sounds like Mexican extremists or something. Well, one of our games at work is we like to pronounce all the Redis commands as if they were words. So that's Bloom filter. Great case for a Bloom filter is usernames. Is this username taken? Well, check the Bloom filter. If the Bloom filter says probably, then no one ever gets to use it. And that's fine. And it's an easy way to manage like 1 billion unique usernames. So that's probably the most iconic example of a Bloom filter. Let's look at minhash. Minhash determines set similarity between documents. Or more accurately, it's a thing that you calculate so that you can determine set similarity between documents. So a minhash takes a document and turns it into a collection of numbers. And then you can use that to compare it against other documents that are collections of numbers and see how similar those documents are. You could use this to detect plagiarism or kids cheating off each other on their exams, that sort of thing, to see how similar their essays are. You can also use it, and I believe Google created this originally, to determine how much a page has changed and whether it's worth indexing again. So let's talk about Jacquard similarity first. How do we compare sets? And this is really a pretty straightforward operation. Here I've got Scalder and Molly from the X-Files, almost. They've been face swapped. And I have put together there's two sets here. One is, they're the sets of which states in the United States they've seen UFOs in. And so Scalder here has seen them in California, Nevada, Oregon, Wyoming, New Mexico, and Ohio, which is where I live. And Molly has seen them in Florida, Kansas, South Carolina, West by God, Virginia, New Mexico, and Ohio. And so New Mexico is Area 51. Ohio is Hangar 18, where the bodies of aliens from Roswell, New Mexico were allegedly stored, which is about an hour from my house. I tried getting in there once, and then I got shot. Yeah. I died twice. Yeah. But anyhow, the way you calculate the Jacquard similarity is actually pretty simple. You create a set from the intersection, and you get its cardinality. So there are two things that are in common between their two sets, and then you divide it by the cardinality of the union, all the things in the sets. So that's 2 divided by 10, so these sets are 20% similar. It's a simple ratio. And so you could do this to see how similar documents are. All you got to do is put all your words in a set from one document and all the words in a set from another document, and it'll just totally work, right? He asked leadingly. No, that won't work because that'll just tell you that they're in the same language because we're using all the same words. And so there's a way that you can build a set out of a document called shingling. And so you shingle the document by taking trigrams and building sets out of those. And so we build a set out of this little document here. We notice to our left, further off into the mountains, a bright glow. Back to our Megatron in the bushes dudes. And that becomes part of the set. And then the next shingle is 1 word over 3 words. So they're laying over top of each other like shingles on a roof. And we build a set up this way until we get an entire document, an entire set of all the trigrams that are used in that document. And then you could take these trigrams and do a Jacquard similarity comparison on those. And that's going to be a lot more accurate. It's going to work, whereas just using words won't. However, if you were like comparing every student's paper, that's a lot of string comparison between a lot of things. That's not a very speedy process. And so what minhash does is it takes these trigrams, these sets of trigrams, and converts them into a numeric signature, a set of numbers. And it does it, you guessed it, by using hashes. And so what we do is we have several hash functions, and we take the entire set and run it through the hash functions and get a series of numbers. And then we select the minimum number in the hash, the min hash. And we do that for the number of hashing functions that we have. And now we've got a set of numbers that represents key phrases in that document. And then we do the same thing for Molly. And then we can do the Jacquard simulator operation against these sets of numbers instead. And this performs much, much faster. So that is min hash. You will notice that my example here, I got 0.5 versus 6 basically versus 2/3, half versus 2/3. That's because I only used 3 hashing functions. You would probably use more than that in a realistic scenario. Again, it needs to fit on my screen. Okay, so the last one, top K, we got 14 minutes and 24 seconds. So this one's a little heavier, pun not intended. Actually, it actually literally wasn't intended, but it came out anyhow. So top K ranks items. And so when you build a top K, a heavy keeper, you say, I want to keep track of the top 5 most frequently used, most common IP addresses to hit my server. Or I want to keep track of the top 5 most popular hashtags on Twitter. And a top K structure is really 2 data structures. It's a heavy keeper, which we're going to go into detail on. And the heavy keeper counts things, but the things that it counts can be eroded by other things coming in, which is why it makes it good for trending topics, because things can come in, and then they stop coming in, newer things can then start eroding them away and replacing them. And then a min heap, which is used to just keep track of the top K items. So if you want your top things, you just say, give me the top things, and the min heap spits them out. A heavy keeper's got, again, these hashing functions with seeds. It's also got an array of buckets, for lack of a better term, for each hash function. So this particular heavy keeper is however wide I've decided to make it, maybe 100, maybe 1,000, and as deep or as tall as however many hashing functions I want. And in these arrays, we have the bucket, and the bucket has 2 values in it. It has a count, which is the second item, and it has a hash value of whatever is owning that count. And so when we go to add something, here's a brand new heavy keeper. So a brand new heavy keeper is nulls and zeros across the board. There's nothing in it. When we go to add something to a heavy keeper, let's say we're going to do a heavy keeper full of words, UFO shapes. Object is a popular one. So we take the word object, we run it through our hashing functions, we get hash values, just like we did with the Bloom filter, just like we did with the min hash, just like we did with the hash table. And we get numbers, and we modulus them with the width, and we get an index. And here we get indexes of 2, 1, and 2. And so what we do is we look and say, well, what's at index 2? Is there a hash value? No. Then we can claim it. Is there a hash value? Well, maybe we need to do something special. So in this case, we claim these positions and increment the count. So object's been added, count is 1. If we add that same value again, it goes through that same process. It goes and finds these locations and says, hey, there's something there. Oh, it's our hash. Okay, just increment the count then. And then if we want to query the count, we just reverse this process. So if we say, how many times has object been added to the heavy keeper? We go and find those indices. We go and find all the counts, and we make sure that the hashes match. If they don't match, we don't do it. And then we take whichever number is the biggest, and we return it. Let's add a different value. Let's add light, another popular UFO shape. So for light, we get different indices for the first 2 rows, and so we claim them and increment the 0 to a 1. But the last one down here in red has something there already. It's got a 1442, and it's got a 1352 that those hashes don't match. So what do? Do we just replace it? Do we throw it away? Do we ignore it? Well, what happens here is there's a chance that 2 will be decremented. It'll be eroded. So whenever there's a hash collision in a heavy keeper, there's a calculation that's made to determine whether we should reduce that count by 1 or not. And that formula is equal to P, probability, is equal to a magic number of B, which is between 1, is right around 1, but greater than 1. And we take that to the power of the count negative. So what happens here is that if we do the math here, we've got 2 items, and the math comes out to be 0.907, so 90.7%. So we've got a 90.7% chance we're going to degrade that value from 2 to 1. But if we had a really big count there, let's say we had 10,000 in there, well, that probability number is going to be a lot smaller. And so what happens is the heavy things are kept. I mean, it's a heavy keeper, so it keeps the heavy things. And the lighter things get eroded away quickly and then get reinserted and get eroded away quickly. And so this keeps things that are flows that are coming in that are more common get counted more. What it means is that the count is horribly unreliable because it's constantly being eroded through collisions. But it'll never be too big. It'll almost always be too small, but it'll never be too big. But the ranking will still be good. So here we've got decay has occurred, and so in row 3, in position 2, we go ahead and decrement it, but we don't change the hash. It still belongs to object. And when we query light now, what happens is we only get 2 hits instead of 3, because only two of the rows actually have values for light. And so we take the biggest value out of all those, which is 1, and then we return it. And when we query the word object, we now get 2, 2, and 1 as our counts back. And we just take the biggest one. And so far, our heavy keeper is still telling us the truth. Now, after this happens, whenever we add something and we have a count change, we go to the min heap and we update the min heap. And so that goes on there with the count. It's resorted and trimmed if necessary. And that allows us to rapidly get our top K items. Redis, of course, has a top K structure. You call top K.reserve, give it a key name, give it the number of items you want to rank. You give it a width of how wide those arrays are. You give it a depth of how many hashes you want. And you give it a decay probability, which is the reciprocal of the number that I showed you earlier. So this is 0.9 here. And then you can call topk.add to add things to the heavy keeper. And then you can call topk.query to say, is this in the top K? You can call topk.count, and it will interrogate the heavy keeper and get a count for whatever value you give it. And you can say topk.list to get the top K items. And that's pretty much top K. I've got a demo where I've used top K from Shock Horror Python. That shows this in operation. So let's see the demo super quick. Okay, so in here, you can look at the code on your own later because I got like 7 minutes and I know there's probably going to be some questions. And it's also the last session of the day and everyone's like, my brain is full, can I go home? So let's do Python. So I've got 2 little things here. I've got app.py, and what Python. Could have been worse. I could have just typed Python. Don't ever go to python.org. Oh, come on. Tells me it's running already. Don't you love it when a plan comes together? Like, what's using that port? Well, let's go ahead and let's run the build. So I've got 2 scripts here. Build.py, what it does is it goes and reads a CSV file with all the UFO sightings in it, and then starts processing them with pandas, and then starts inserting them into Redis. I remove all the stop words so the most common words aren't like a, and the, and stuff like that. And so what this is doing up here is it's reading all the various UFO sightings, pulling out the relevant words, and then shoving them into a top K structure. Over here, this is just a little JavaScript app, which allegedly, we'll fix this. Screw you, hippie. Hey, look, it worked. We'll just keep doing that until we run out of ports. Okay, So now if I refresh this page, oh, it's pointing to 5001. There we go. See, this is why I needed the time for the demo. So what you see here is I'm hitting it every single second just to say, give me an update. I'm asking Redis in those top K structures, what are the most common words used in UFO sightings? What are the common UFO shapes? And I think light and lights is kind of course, that's probably the most common, right? It's like I saw a light in the sky. So that's my little demo that shows this top K structure in action. The cool thing here is these counts are going to be off, but the ranking is pretty solid. And the fact that lights and light both show up and then object and sky, these are all the words you would expect to see in UFO sightings. And for shapes, I like that light and object and unknown and formation are all shapes. It just always makes me laugh. So, and now my MacBook battery is kicking up, or fan's kicking up. So let's go ahead and, I got a few more slides. All that code is out on GitHub. You can go play with it yourself. It honestly needs to be updated. I should create a Java version is what I should do. That would make all y'all happy. So here's a bunch of resources. Don't feel like you got to take a picture of this slide necessarily, although you're more than welcome to. Bloom filters by example is where I got some good pointers on how bloom filters work and more importantly, a good visualization for them. The bloom filter calculator, I mentioned that there's one online. That is it. Min-hash tutorial was super useful in putting together how these things work. HeavyKeeper, an accurate algorithm for finding top K elephant flows, is a white paper that I read so that you don't have to. Whoops. The UFO Sightings database, I got the data set from data.world/Timothy Renner, and go out there and check it out. It's a lot of fun. It is really fun data. If you want to go to the source at newfork.org, which sounds worse when I say it out loud, you can go check that out. Meet Top K is a blog post we have talking about Top K. It's a few years old now, written by one of my coworker, Ariel. And then you can go to Redis Bloom information at redisbloom.io. And you can get Redis Insight, which I didn't actually show here, but it's a GUI for Redis at redis.com/Redis Insight. And obviously, I work for Redis. We got a Discord server. If you have questions, you can get on there, and I cannot answer them. We got free classes at university.redis.com, and you can get a cloud version of Redis at redis.com/tryfree. We like you to get the cloud version because that turns into paying customers, and we all like money. More importantly, this is the link you all really care about. This is all the codes and slides out on GitHub, so you can go play with it. Go ahead and scan the QR code. It will never give you up, nor will it let you down, or run around and take you to some site it's not supposed to. So, and that's what I've got. Let's go to Q&A. We got, what, 2 minutes? Could you provide example hashing functions for these data structures? Let me, hang on. I'm still in presentation mode. End show, there we go. Yeah, so I actually have implementations of all of these data structures in various languages in the GitHub repo. In them I used, I don't remember which ones I used. I used murmur hash, I know, for the JavaScript implementation. I know I did one in Java, I think I did one in C#, one in JavaScript, and then I think I ran out of time when I was doing this, but there's some examples in there. In JavaScript I did a bloom filter and top K. So, and in that case I used a murmur hash. You could even get away with building your own hashing function using like exclusive OR and stuff like that. So these don't need to be terribly sophisticated. A lot of hashing functions, like what a cryptographic hashing function does is it's trying to make small changes to the data, create random variations in the output number. That's to make it secure, right? So that you can't tweak the number by 1 and guess. But for speedy ones, it doesn't really matter that small changes to the data make small changes to the hash value. They just need to be unique. Or you need to minimize collision, so they need to be evenly spread. And so These aren't to the same standard. So this is one of those things where you can actually write your own and not get in trouble. So, yeah. But I used a murmur hash specifically. What's my favorite UFO sighting? Well, I actually saw a UFO as a kid. And so that's probably my favorite. It's true confession time here. I remember I was in my trailer, going to my bedroom when we lived in a trailer. And I laid down in bed, and I looked out the window, and I saw like this disc that had like lights around it. And it was like kind of shaped like this a little bit, and they were colored squares of light rotating around. And I remember as a kid thinking that when I'm an adult, I'm not going to believe this story because I'm going to think that I was dreaming it because I was in bed when it happened. I think what it was, honestly, is it was probably a blimp. I lived on the path of the Goodyear blimp where it would go up and down to sporting games in central Ohio. So I think it was just the Goodyear blimp running things on its screen that went past my window. But that's my favorite UFO sighting of all time. Honestly, Megatron in the bushes is a pretty good story. And so I like that one a lot too. So I'm all out of time. I know everyone's got like alcohol to drink or something, I think is what's next, right? That's what I'm going to be doing. So thanks a lot, everyone, and have a good rest of the week in the conference.